Good afternoon, everybody. We're excited to be here for the third day of our October webinar series. If you have any questions for our audience, if you have any questions, please feel free to type it in the Q&A section while the presentation is ongoing or at the end, and I'll be happy to read out your questions. The title of today's presentation is Mitigating Data Poisoning Attacks in Federated Learning. And the presentation will be delivered by Dr. Euclides Neto, a postdoctoral research fellow at the Canadian Institute for Cybersecurity (CIC), located at the University of New Brunswick. Dr. Neto is a computer scientist with a master's degree and a PhD in artificial intelligence and its applications to aerospace and safety critical systems. He has been involved in different AI initiatives involving safety, security, and aerospace projects. Dr. Neto, please, you have the floor.
Thank you. Appreciate that. Thank you for the introduction. So hello, everybody. Very excited to be here with you all today. So my name is Neto, Euclides Neto. I'm a researcher here at the Canadian Institute for Cybersecurity. And today I'll be talking to you about mitigating data poisoning attacks in federated learning. So let's get started. Okay, so I'll make a brief introduction on the topics that we're going to be discussing, like the important topics for our proposal. And after that, the motivation for our, for this particular initiative, the goal of that. And then we also need to highlight some important points on federated learning, data poisoning, model interpretability, and then after that we present the most important concepts of the proposal, and then finally the results, the experiments and their results, and finally the conclusion as well. So this is a kind of new endeavor, so we're very excited about the initial results that we are getting here. So just be presenting all the details here. So first of all, machine learning and deep learning, it's being used like in so many different applications, everywhere, all over the world. So we have like very successful cybersecurity applications, healthcare applications, agriculture, transportation, you name it. So it's been very, like there's a huge potential here to transform people's lives and then businesses around the world in so many different ways. There's a huge potential here, and then of course, naturally, a lot of people, a lot of companies are investing a lot in AI in general, not only machine learning, deep learning. But at the same time, there are many challenges to be faced, right? There is we have to face many obstacles in order to make sure everything is performs well, is well deployed, everything works properly. And examples of these challenges are the performance, ensuring that we have a good performance in the in the operations, right? Interpretability. So just basically, like, how can you understand the responses the models will give us, right? We give us in terms of the reasoning, right? The reasoning behind scenes, and also privacy. Privacy is also a very important concern. So in some applications, we don't want to disclose the data that we have. So privacy becomes an important issue here. And then this requirement, let's say the strong requirement for privacy, it motivated the development, the conception of new ideas, new proposals, and new methods. And among those methods, we have federated learning. So that's the motivation behind scenes for federated learning. Even though there are some question marks, people are investigating how secure we are regarding like how private the information, the data is regarding the usage of federated learning, but that's the motivation here. And this process, let's say, is basically we have a distributed process in which multiple entities, they are part of the learning process. Basically, we have a distributed data set in which multiple entities, we call them clients, they share a piece of the data, and then we just want to learn. We have to want to have a global model that learns from all entities without disclosing the data, right? That's the challenge. So in order to avoid disclosing the data, what we do is we disclose the knowledge, which means basically when you're talking about deep learning, for example, we disclose the weights, the model weights, and you combine them in a centralized way. So that's a different approach to learn is very interesting because, like, when you think about the optimization process or the search process for, appropriate weights, is a completely different thing because instead of like walking towards a really good region in the search space, in the multidimensional search space, we are actually like taking steps towards different directions depending on how the data set will, the information the data sets have, right? The data sets for all clients. And then that's the way we move forward in the learning process. So it's very interesting, of course. And again, it's very powerful, but at the same time, there are many challenges. However, there is a big caveat here for the systems and the applications we have. We assume that the data is good, right? All applications we have, we assume that like the model needs to learn from the data, and then the data is the let's say the perception of the reality we have, the perception of the universe we have, and then the model will be able to learn from this data and then be infer things in the real world. But the thing is, if the data is not good, I mean, if the data is compromised, the whole process is compromised, right? If you cannot trust the data, we will be compromising our learning process, right? So that's a big problem here. So based on that, with this problem, facing this problem here, the goal of this initiative is actually to propose an approach to mitigate data poisoning attacks using federated learning and model interpretability and aggregation and weights evaluation. So I will talk about those topics as we go forward in the presentation. But the question here is basically, how can model interpretability protect the learning process and do that in a federated environment, a federated approach, right? So that's the question we want to answer in this particular effort here. Okay, back to federated learning now. Again, we have multiple entities, multiple clients collaborating to this learning process, and then you have the coordination of a central server. So the central server is responsible for collecting all the knowledge and then find a way to combine all the knowledge and then provide a global model, update the client with a better model, as to say, right? A model that includes everybody's knowledge. And then the raw data is stored privately or locally, and then only the knowledge, which means the weights, mathematically speaking, the weights are disclosed, are shared. And then these weights are combined in order to build this model, right? And then when we talk about data poisoning again, we might suffer some attacks in our data sets, which would compromise our learning process. And then you have several ways, like several types of attacks. And here we have two examples. We have label flipping and data injection. And sometimes they come with different names, but basically label flipping refers to, we have our data set, suppose we have a classification problem, we have a data set that helps us to build our classifiers, but then there's a vulnerability in the system, and then someone gets there, breaks into the system, and then changes the labels of, a set of instances. And then it just like confuses the model in order to identify what class instance belongs to, right? A similar thing is done with data injection. The difference is here we just inject data. It could be anything. It could be a randomly generated data, or something like more like, let's say, malicious and coined for this particular environment, let's say. But the idea is we just inject data. It could be noise, could be anything, and then we assign it to assign labels to it in the way we want to, right? So once you have this kind of attacks happening in the data set, and you don't even know it's happening, or you don't even know we have this kind of malicious data there, it's kind of difficult to deal with, right? So when you think about the way it works, we have different clients, we have weights being uploaded, and then updated models or up-to-date models being downloaded, and you have many rounds. We have the clients interacting using weights, and then you have, for example, here you have two classes, class A and class B. But then if there is a particular client or a set of clients with a vulnerability or a set of vulnerabilities that can be exploited, and then someone breaks into the system and then starts to mess around with the data, we can have, for example, here's label flipping. We can have class A represented as class B and class B represented as class A, right? And then in the learning process, the knowledge that you're going to share, we're going to include this, right? We're going to include this instances saying, hey, this is a class A, even though it is not, right? So that's something that can be harmful for the learning process. And also for data injection, it's, again, we have class A, class B, but then you just include noise to the system, and then we can, label it as we wish. And then that's going to be also a problem, right? Of course, it depends a lot on the application. Don't get me wrong. For example, if you have, let's say, thousands of clients and just one client with a small data set suffer this kind of attack, then the consequences tend to be, let's say small, or at least, we can deal with that. But then when you have many attacks or many clients with compromised data, or a big part of the data set, the whole data set compromised, can be very harmful. Okay, so we have these problems here. It's kind of difficult, right? If you're not able to check if the data is, like everything's correct, everything's all right. And so how can you face this problem? How can you face this problem? How can you mitigate these attacks and then make sure the learning process is, kind of resilient in terms of changes in our data sets? So that's the question we are trying to answer in this effort. So in order to answer that, we start to brainstorm and test different methods and approaches regarding model interpretability. So here we consider this let's say a very important aspect of this initiative. So the question is, once you have a model that is able to classify something, it has a good accuracy, has a good performance, let's say, should you trust it? It's very difficult to know if it is, if you can trust the classification of a model without understanding how the model is reasoning, which is very difficult, right? Don't get me wrong, it's very difficult to go there to know all the details, and it's okay, so that's the way the model is thinking, and then we should trust it, right? So it's very dependent on the application. And then to deal with that problem, we are using LIME, which is the local interpretable model agnostic. It's let's say a platform, it's a very handy, very useful platform that uses local interpretability to understand how the model is reasoning overall. It's one of the most popular interpretability efforts out there. There are other pretty successful platforms as well, but then LIME is one of them, and it's model agnostic, right? So you can play around with different, models, different problems, different concepts. So that's very, very neat. So I just give an example here. It's very standard example, but I think it's very illustrative. Is important to show you here, to highlight the important aspects. So suppose you have a problem in which you have to classify wolves and dogs, wolves and huskies, right? And then you have, let's say, this is the data set we have, and then we have a model that has already been trained, and then you just present these features to the model, and then the model says, okay, so we start to classify them. And then in this classification here, we had 5 images with the right label and just 1 with the wrong label, right? Which is amazing. I mean, like if you have, like thousands of images, let's say, we would have probably a good performance, good accuracy and everything. But then when you start to take a look at the reason why the model is classifying wolves as wolves and huskies as huskies, we can see that the explanation is it has something to do with the background. Because in the training data set, in the training set that we had, the wolves were in a snowy background, like it had a snow scenery, right? There's snow in the picture. And dogs, they had like grass or something else, right? So even though we are not really, we don't really know what the model is doing, what it's doing is it is classifying snow and grass or other things, right? And it could be very dangerous. It could be very dangerous depending on the application, right? So you need to understand what's going on behind scenes. Same here. It's another standard example. We have a dog playing the guitar, and then the model classifies it like you have several classes, right? And then you have the electric guitar, the acoustic guitar, and the Labrador. And these are the explanations for that. So that's the guitar. You have the the guitar frets there, and then we have acoustic guitar, where you can see the body of the guitar, and finally the Labrador, you can see the dog there, right? Okay, so based on that, our initiative is the Interpretable Poisoning Mitigation IPM. We are again we have let's say preliminary and promising results, and then basically we have an aggregation proposal to mitigate the poisoning attacks to our data set. So basically, we are not really focused on what we learn, even though we are, of course we are, but then the emphasis here is how, like based on how we learn, how the models learn and perform and classify and behaves, let's say. So this aggregation depends a lot on interpretability, and like it's applicable to ML problems that can be evaluated by humans, which means we have this, like it's difficult because some problems are difficult to do that, but then generally speaking, we need to be able to explain why we are classifying as such, like, as let's say wolves and dogs. We need to explain why we're doing that, and it is applicable to any type of data, right? In terms of the requirements, we have the reference set, which is basically a set of instances classified and explained by a human, by a SME, by a subject matter expert, which highlights would illustrate the right way to think. If like that's the closest we can get from a good explanation for a classification. And also we need a similarity score or similarity measure to provide this score that would calculate how close our model is explaining something compared to the SME's explanation, right? So we want the models to have a good performance, but also to explain something in a similar way of the, compared to what the SMEs explain, the way they explain it. So that's the pipeline we have. Again, we have the clients interacting with the system, and then the centralized server, we have, first of all, the reference hash. Number one here, have the reference hash, which basically is you have a human SME that's able to classify and explain this instances, the reference hash. And after that, we have models for our clients. These models, basically, we have the weights, which is, upload the, let's say the standard or and model with random parameters, and then you just upload these weights to this particular models, and then we use them in order to classify different instances in the reference set, and also to extract the explanation, use LIME. So use LIME to do that. And finally, number 3 and 4 here with the explanations, we just compare or evaluate how similar, how close we are in terms of the explanations. And based on this this similarity scores, we just prioritize different weights, different clients, in order to combine the systems, and then combine the weights, and then provide a different system with different results, hopefully, right? So that's the idea behind scenes. And now let's go to the experiments. So we use here a pretty famous data set, cats versus dogs. Again, it's the standard data sets out there, and it's pretty handy to it's composed of several images of the cats and dogs, and the task is to classify different, given a dog, you have to say it's dog, given a cat, you have to say it's a cat. And then it's very interesting to use images in this particular context, because it's like easier to understand the explanation, right? It's easier to take a look and say, okay, so that's clearly a cat or clearly a dog. Sometimes, depending on the data, it's kind of difficult to do that. We use a NVIDIA GeForce. Yeah, we use a kind of a nice hardware there to run experiments quickly, and we use PyTorch here to do that. So there was a deep net, and then the goal is basically, given this distributed classification task, let's mitigate data poisoning attacks. Let's see how our proposal behaves or how it performs, right? We have 3 different phases here: data split, attacks, and results. So I'll just go over them, explain them to you. In terms of the data split, we have several images there in this data set. If you have a chance to download those, you see that we have several images. And then we just randomly split them across 4 different clients, 4 different data sets. So you have like, just as a first experiment there, have different numbers. And also you have a reference set and a test set of 1900, and then a reference set of 100 pictures or images. But in this reference set, as I was mentioning before, is actually we have the pictures of cats and dogs, and then the explanation why like this picture includes the cat or why this picture includes the dog, right? So it's basically the explanation that the SME would present for any type of data, right? The explanation why we're doing this. And here we are using masks. So basically you're just identifying the pixels that would represent the class that we want in that particular the particular image, right? Of course, there are many different ways to do that, but then that's the way we are doing. That's human labeled, so we are labeling that manually. And then you have 2 attacks again: label flipping and data injection. For the first case, you have 80% of the class cache flipped. In the second case, we have 40% of extra cats added, but just noise with the cache label assigned to it. So in terms of the results, here you see this the results for our accuracy. The blue bar represents the Fed average, which is the widely used aggregation method, and the red one is our proposal. So we can see that in the normal scenario, we would have the let's say standard approach outperforming our proposal. However, when you take a look at flipping and injection, we see that our proposal outperforms Fed average, right? So that's a very interesting result that we got there. And also the same for F1 score, that's pretty follows the trend. And then if we can get a bit more visual regarding the results, suppose you have this picture here, just an example that I took from the test session. So the SME explanation, let's say that would be the pixels that would represent a dog. After 100 rounds, Fed average could identify a dog because of those pixels, and our proposal because of these pixels here. So the thing is, we are taking a bit of the background, you can see there. However, most of the pixels presented by the SME they are being captured by our proposal, right? Same applies to cats. We have like Fed average after 100 rounds, identifying different pixels, but in our case, you are able to select the pixels that would represent a cache, right? Okay, so there are many sites here in this initiative. We have like things to explore because there are some questions regarding how can you actually use, like how can you actually define the explanation? It's kind of a difficult problem. Similarity measure, how can you use different contexts, different scenarios, efficiency. There are some questions here. And then in conclusion, we have this, this proposal using interpretability to mitigate this challenge, these problems, these attacks, and we can apply this problem to this proposal to different contexts, different problems. And then there are several future steps that we intend to take. So for example, different models, different tasks, different similarity measures, and also how we can deploy it effectively in different contexts. So that was it that I have for today. Thank you, everybody. If you have any questions, I'll be more than happy to take them.
All right. Thank you, Dr. Neto, for the very informative presentation. At least I learned something new about cats, dogs, and wolves. We have a few questions here for you. I'll read them out at once, all of them, and you can respond to them in no particular order.
Okay.
So, okay. The first is, why do you think the proposed strategy was able to identify relevant pixels? And the second is, what are the main challenges to deploying the system? And the final one is, what are the next steps you intend to take in this initiative?
Okay, yeah, this is they are very interesting questions. So first of all, regarding the way we capture or we identify the pixels, it has a lot to do with the the reference that you're using, right? So we are diving into the like we are basically using knowledge or SMEs explanation in order to tailor our systems to our needs, which means that depending on the application, again, it's very interesting investigation because there are many challenges, but also it's very promising because when you think about the explanation of SMEs, we can also make our systems biased, right? We can just like direct our systems to a direction that we don't really want to go, like a path that we don't really want to go. But then it's definitely dependent on the reference that we're using. And then the reason why we are selecting or highlighting these important pixels is just because we need to be close to what the experts say, and then in order to do that, we just using the optimization approach, this particular measure or this particular score as a way to move forward in the search, right? So that's basically a natural result. And then of course, again, we are using images here, but then it would work for audio, for text. However, it can be difficult to see, right? It can be difficult to evaluate, to measure. That it can be difficult even for experts to say, okay, it's clearly class A or class B, right? It's very dependent on the problem faced. And the other question regarding the I'm sorry, I don't remember the second question. It was about
the second question is, what are the main challenges to deploying this system?
Oh, sure, deploying. Okay, so yeah, I mean, we have the big question mark we have here. That's something I'm working on at the moment is the processing time, right? So we have kind of in order to compare or to evaluate this this interpretations or this way of reasoning, we are dedicating a lot of time. We have to dedicate a lot of time in order to make it like, you know, to work it to make it work properly. So it is kind of difficult in order to understand how we can improve the processing time, let's say. So that's where focus at the moment. I suppose that's a big question mark. Once you have a good timing for that, like a good processing time, can reduce it, and we sure can, and we'll be able to you know, like that's the big obstacle regarding deployability, right? Once you know it, we can deploy it more effectively or more easily. And finally, regarding the future steps, we have many things to explore, right? So for example, we can combine not only the capability of mitigating these attacks, but also have different kind of factors to be included. So for example, we know that some clients may be more vulnerable because they are not with the, you know, like the most up-to-date software version or firmware version. They did not install, they have installed patches, for example. So they can be also scored based on that because they are more vulnerable to these attacks. And then this can also be included in the system, right? In the whole calculation, the whole prioritization of the weights. So basically, we have many different things to explore. What's moments we are focused on the let's say the performance of the system, make sure everything works well. And once we get to a stage and we just say, okay, so it's running really well, it's really sound now, then we can move forward and then try to explore new concepts that can be included and also be included in particular applications, right? So you have several applications in healthcare and everything involving cybersecurity, but then healthcare, and then you have transportation, have many other fields, and then the finance sector, and then we want to tailor our applications to those particular fields. So, you know, long story short, that's pretty much what we are focused on at the moment.
We have one final question for you today, which is, do you think this proposal can be applied in unsupervised learning?
That's a very good question. That's a very interesting question. Well, regarding unsupervised learning, like things change a little bit. Things change a little bit because here we are, for example, we are talking about label flipping, right? And then as we are talking about label flipping, we are not really having a label in unsupervised learning, right? However, we are also vulnerable if someone gets there and then includes a lot of noise to our system, right? And then the noise will be like maybe closer differently, or I don't know. So that's a very interesting question. That's something that we haven't worked on, but then we definitely will take a look at it. So as long as we can interpret different ways of classifying or grouping different instances, we sure can use our proposal.
All right. This brings us to the end of today's presentation. Thank you everyone for joining us, and see you again tomorrow.
Thank you, everybody.
All right, bye-bye.